So remember that we were looking at domain and range, and we talked about domain. If you're looking at a picture, you want to scan from the left to the right. If there is no point furthest left, you're going to use a negative infinity. If there is no point furthest right, you're going to use positive infinity. Okay, so this graph starts right here with that point. And they put the big fat dot there just to indicate that we do include that point. So the domain starts at -6. And remember we said you're going to use a bracket if there's an actual point that corresponds to that x value. And there is, so I'm using a bracket. And then it goes on forever. So I'm going to say to infinity. Now range, remember you scan from the bottom up. If there's no bottom, that's when you use negative infinity. And how can I tell there's no bottom on this one? Yes, because of the ends, you can see that it's continuing. So there is no bottom. Is there a highest point? Yes, it's right there. And remember that you're not going to see a big, fat, solid dot there. It's just going to be a smooth curve. They only do that at endpoints. So we do have a point right here it's the 0.31, and since I'm looking at range right now, I'm going to say that we end the range at 3, and then you've got to decide bracket or paren. Which one on this one? Yeah.
Why is it negative infinity if it goes to -5? Oh, wait.
Bottom up. You're looking at the y values. There is no bottom. That's when you use negative infinity. If there was no top value, if it just kept going up forever, you would use positive infinity. Okay? But there is a highest point. It's right there. And so we're going to say that the range stops at that y value for that point. Okay? You're separating out the x's and the y's. That's what gets a little confusing. Yes, ma'am?
So what if we put 1 instead of 3?
Oh, thank you. Yes. Yes, absolutely. Just because the teacher says something doesn't mean she's right. Okay. Yeah.
And if there's no dot, we always assume that it's a close?
Yes. Yes. Remember, the only time you're going to see closed dots is at end points. And they're just making the point that there is a point there. You could see open circles anywhere, but not closed. They won't do that with closed dots. They only do that at ends. Anybody else on that?
Can you say the definition again when it goes up?
Yes, and I wrote this out in the key as well. So, and just because of time, I'm not going to write it out right now. Okay, Hope? Okay. But if you are looking at domain, you want to scan from left to right. So if there is no leftmost point, then you're using negative infinity for domain. If there is no rightmost point, you're going to use positive infinity for domain.
Thank you.
Sure, and that's similar for range, except that's from the bottom up. No bottom, negative infinity. No top, positive infinity. Otherwise, you're saying where it stops. Okay, now, this might be the first time you've seen a graph like this. And really, in 1105, we just kind of introduce you to it. The students that go on and take pre-calculus algebra are going to learn how to find these things that are called asymptotes. This one is called a vertical asymptote because it's a vertical line. And it's not really part of the graph, but what it's showing is that as this graph, as the x values get closer to whatever the x value is here at this red vertical line, as the x values get close, your graph is either going towards negative infinity, or if it was shooting up towards positive infinity, then that's something called an asymptote. Vertical asymptotes, the graph will not cross. Now, you can have horizontal asymptotes as well. We'll actually look at a couple graphs later that, probably this week actually, that include a horizontal asymptote. And those might cross somewhere, like, early on, but not at the ends. Yes, sir?
The left and the right are two different graphs.
They are the same function, but they are two different pieces, and you do have to see that because we're going to have to make a break in our domain. Okay, I don't know if that's what you were thinking, but this is one set of points. It's a set of points that comes down like this and goes towards negative infinity. It's like you've got this vertical line, and it's getting closer, 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 but never crosses.
And it doesn't meet up with the other line.
That's correct. That's what happens with vertical asymptotes.
But the horizontal is
We'll worry about them when we get to them. And again, you're just going to see them and understand that's what that is. Okay. And then if you were coming from the right towards this red line, the points are also shooting towards negative infinity, but they won't cross somewhere down there. That's what the picture is telling you. Okay, so we're going to say the domain, okay, is there any leftmost point? There is not, so that's when you're going to use negative infinity. Now, this is the first time we've seen this. We're going to stop at 2, but there isn't any actual point that has an x value of 2. So that's why I'm using a paren.
That's because the vertical.
Yes, exactly. Okay. Now I want to make sure everybody hears me correctly on this. So if I need to repeat it or you need to ask me a question, please do. I will have students who will, for some reason, they'll think, if we don't want to include 2, then we got to start at 1 or stop at 1. See, there's points in between. Oh, that's not a 2. I'm sorry. Really confusing you today. I'm sorry. To 1. Yeah, to 1. So what I meant was there are points between 0 and 1. There are values down here, see? Okay, so you're not going to go, oh, it can't equal 1, so it only goes out to 0. No, it goes as close as you want to be to 1. This is kind of a difficult concept. Okay, I can give you an example. 0.999999. Okay, that's not quite at 1, right? But it is in the domain. There is an actual point somewhere that has that x value. Is that making sense? Does anybody have a question about it? Yes, Maya.
So when do you actually, for the domain, it's the negative infinity, which is on the left side.
And then we're going to stop at 1. We're not done.
Okay, and the curve, when the curve starts, usually that's how you would say.
Yes, it doesn't start, right?
No.
So that's why we say negative infinity. But it doesn't go past 1. But now we pick up on the other side, there are points from 1 forever, right? Okay, so you're going to say 1 to infinity. All right? Now, the range is really weird because you're looking at this broken graph. There's 2 pieces. But remember, when you're giving the range, you're giving all of the y values that have at least 1 point. So think in the downward direction. Is there any bottom? There is not. So we're going to say negative infinity. In fact, a lot of times there's more than 1 point that goes with a particular y. Now, even though you're looking at this broken graph, there's no break in y values because you tell me any y value you want, and I will go high enough if I need to and show you there's a point there. So no matter where you are, think of coming up. No matter where you are, you've always got y's. You see them? Okay, like when you get up here, there's some over here. If you're down here below -6, you've actually got 2.
What about on the other side?
Now remember, you're looking at y. So you tell me any y value that you want, and I will find you a point. At least 1. There might be more than 1.
But for the other graph also?
You're looking at x. If you're thinking over here, you're looking at x. Remember, we're looking at y. And we're thinking whether or not there's a point there. There isn't over there, but there is over here. Okay? And so we're going to say it's negative infinity to positive infinity is the range. All right?
Because it keeps on going.
Yes, right. It keeps on going up. There's no bottom. There's no top. And you cannot find a y value for me where I can't give you a point, at least one, sometimes 2 or 3.
So we don't
Okay?
have to do a union?
No. Mm-mm. The only time you have to do union is if there's a value that is not in the domain or the range. Okay? So just because you're thinking that way, let me just draw a little picture here. You know, if I had, I forgot to justify my board. I'm trying to draw 2 pieces here. Whatever. See, here's a break in y's, right? You see it now? So that one would require 2 intervals. I've got to take a little commercial break here for a moment. Intermission, I guess. I meant to do this. There's so many things to do to get ready for the video in addition to class. I forgot to do this. These boards, some of them stay oriented and some of them just don't. This is really exciting to the folks at home, I'm sure, to watch me touching these dots. Okay. All right. Okay. Now, remember last week we talked about what a function is, and I tried to get you guys to get past thinking, oh, it's a function we plug in. The way you want to think about functions is input, output. And that's going to help, I promise, if you'll think about it that way, when you're figuring out what the domain is when you're given a rule. What you're going to want to think about is, can I put anything in and get a number back? So we're going to write this down. The domain, when it is not given, okay, what you need to do well, first, let's write this. Domain, when it's not specified, is all real numbers that produce real numbers. I'm going to give you a really quick example after you write that down. It's all real numbers that produce real numbers. Okay, I mentioned last week that your calculator is a function machine. If you press the x squared button, you can do that all day. You could do that for the rest of your life and never repeat a number. You could just keep plugging in different numbers all day long and keep hitting the x squared key, and you would always get something back. So what's happening there is real numbers are always producing real numbers when I hit the x squared key. Does that make sense, kind of? Okay. Now, I'll show you a key that doesn't work. And we're going to get into the LOG and LN at the end of the semester, and those don't work for everything. But I'm going to give you one you already know. It's x to the negative 1, which is reciprocal. So, like, what's the reciprocal of 2? No, that's the opposite of 2. 1/2. Okay, so let's do 2, and we'll hit the x to the negative 1 key and hit enter. Now it's giving it to me in a decimal form. That's the fraction 1/2, right? Okay, if I plug in a lot of things, I'm going to get an answer back, and I could see what that fraction is. Like I just plugged in 5. Okay, I hit the reciprocal key and I got a number back. What number doesn't have a reciprocal? 0. Look at what happens. 0, x to the negative 1, I get an error. That's a real number. 0 is a real number, but it's not allowed. It's not allowed because it doesn't produce a real number. So that's what you're about to do. is you're going to look at a rule. That one's simple because it's just reciprocal. That's all it is. But you're going to look at the rule and ask yourself, is there anything I'm not allowed to plug in? If there is, then your domain is limited. It's not just negative infinity to infinity. So that's what we're going to work on now. We're going to kind of do general categories for this. Okay. So what you need to do is you need to find any values or intervals of numbers that do not produce real numbers. So like I said, we're gonna kind of look at general categories here. Getting a little warmer, you guys. I don't know if that's why they had the door open. All right. So if you have polynomials, the domain is all reals. I'm going to give you some examples. If you have a polynomial function, the domain is all reals. So here are some examples of polynomials. F of x equals 3. That is actually a constant function. It is very misunderstood. This is one you'll probably be asking me about as you're doing homework, some of you. But if you understand the input-output, then you'll understand what this is saying is no matter what your input is, assign it the number 3. Pair it with the number 3. Oh, even weird numbers like pi? Yep, pi gets paired with the number 3. So that's always the output. It doesn't matter what the input is. All things work. All right? Next week, when you have to review lines, you're going to remember that this is a horizontal line. Okay? Another example, and I'm going to give it a different function name. I'll call it g of x. Negative 2x plus 1. That's actually linear, which you're also going to be reviewing next week. So now, think in terms of input and output. If I plug a number in, you give me any real number. Integers, fractions, square roots that won't reduce, weird numbers like pi, anything. What is this saying to do to that number? Multiply it by negative 2, still real, and then add 1, still real. So it doesn't matter what I plug in, what my input is, I'm always going to have an output. And so all reals are allowed. Okay, let me give you a couple more. H of x is x squared minus x minus 5. That's called quadratic. That is a quadratic function. We're going to study these in Unit 2. You're going to have a little bit of the basic kind next week. But what do we do to our input? We square the number, we subtract that number, and then we subtract 5. That always produces another number. So all reals is the domain. And I was just going to give you a crazy example. J of x. What if it was x to the 100th power minus x squared? Okay, we don't really have a name for that kind of a function, but I wanted to point out how you know this is a polynomial. If you only have one variable, which we do, x, and your exponents are positive integers or counting numbers, then you've got a polynomial. If this had a negative 2, it wouldn't be a polynomial. If this exponent was a negative 2. All right? So all of those, the domain is all reals. Okay, now what about absolute value functions? Well, the only ones we're going to study in 1105, if you look between the absolute value bars, you're only going to have a linear expression. So the ones we're looking at will look like, I'm just going to do this one with an example. Absolute value of x plus 1, and then subtract 3. So what is that saying to do to your output? First, add 1. Whatever you get, take the absolute value. What does that mean?
The positive.
Yeah, make it positive. If it's negative, it becomes positive. If it's positive, it just stays the same. And then you subtract 3. Isn't that always going to produce another number? So that means the absolute value functions that you're going to encounter in 1105 are also have a domain of all reals. Now, if you have an odd root, for example, f of x equals the cube root of x. That's read the cube root of x. Okay? For example, let's find f of negative 8. That's the cube root of negative 8. And so the answer to that question is you think, what number do I have to cube to get negative 8? Negative 2, right? Negative 2. You know, negative 2 times itself 3 times is negative 8, right? So the cube root of negative 8 is negative 2. Now, there is a way on your calculator to find roots. Okay, we're not really going to get into that right now. But I promise you, if the root is odd, this number under the root, under the radical sign, can be anything that's a real number. And you could find an approximation in your calculator for it. You would get a number. There's no problem value. So odd root functions are also all reals. Their domain is all reals. So what we did there was we covered all the types of functions you're going to encounter in domain and range homework where the domain is all reals. Okay? So anytime it's polynomial, the absolute value functions, and odd root functions, all reals. So now what we're going to do is we're going to look at the problem type functions. And these are just 2 examples. We will be getting into some others that don't have all reals as their domain. But even root functions, for example, we're going to look at a really basic one, the square root of x. Remember, if there is no number in here, it's understood to be a 2, which is a square root. 2 is an even number. That's what I'm talking about. 2, 4, 6, 8. Who do we appreciate? Okay. The even numbers. So, there's a problem here, right? What's the problem? And you guys actually encountered this in your first homework. Some of you were a little ahead of where we are, and so you were thinking, oh, square root of negative 1 is I, and so we do get answers. Why is my answer coming out wrong? Well, because you were solving over the reals. You're only solving over the reals in the first unit. Okay? So we can't calculate this in the real numbers. That has no value in the real numbers. There is no number in the reals that you can square and get a negative value. That's impossible. So we can't plug anything in that's negative. But you have to be careful because sometimes you're going to have ones that aren't just x. So the domain for this particular one is 0 off to infinity. And what you're going to need to do is you need to find, or let me say solve. Let's see. I am not tall enough to write this, but I want to say the ones you guys are going to come across will look like this. You might have a number times x plus another number. So it's actually a linear expression under the square root. Now, there are other things possible. It's just that you're not going to see them in 1105. In 1105, that's as awful as it's going to get. All right? So you need to solve what makes ax plus b greater than or equal to 0, which is called a linear inequality. There, all we're going to have to do is solve for x, and then we'll know. So we're going to take a look at that in just a minute. I just want to get these general categories, and then we'll do some examples. Rational functions. Okay, for example, we've already looked at one of these with the calculator. 1 over x, bless you. That is that reciprocal key that I was referring to. Now, is it okay to plug in negatives? Like -3? Do we get a, is that producing a number? Is that a number? Yeah, that's a number. -1/3, right? That's -1/3. Negatives aren't a problem. It isn't negatives that's a problem. What's the problem? The denominator. Yeah, you can't have 0 in the denominator. So what you have to do, let's write that down. You cannot have 0 in the denominator, meaning the entire denominator can't equal 0. And so what you're going to use algebra for is you're going to find the values that make the denominator equal 0. And you're going to include everything but them. Everything except those. I'll give you an example in just a minute. I just want to kind of get the categories down first. So with even roots, and I gave a square root as an example, but it would be exactly the same as 4th root or 6th root, 8th root or whatever. You're going to solve this inequality, and this gives you your domain. So what we're doing there is we're using algebra to answer another question in algebra. This is algebra, right? Solving an inequality is algebra. You're using that to answer this question about domain. Okay, on the next type of problem, the rational functions, you're going to use algebra. You're going to set up an equation, and you're going to solve it. That's part of why you practiced in that R module, okay? You're going to solve it. You're going to find out what numbers make the denominator 0, but they're the only ones that aren't in the domain. So this gives you the domain up here. This gives you what's not in the domain down here. So we'll do some examples now. Oh, and I should say here, let me do a picture of the domain. The only problem value for x, just plain old x in the denominator, is we cannot use 0. We can use any other number. And so what we do is we put back-to-back parentheses at 0, but this is a picture on the x-axis of all the other numbers. So anything up to 0 works, anything after 0 works, because I can plug it in and get a number back. So here's your domain. It's -infinity to 0, union 0 to infinity. That's throwing out, remember paren means don't include. So what that's saying is there's no bound on the left for the numbers that we can use in domain. They all work up to 0. 0 doesn't work. Come on the other side of 0. Then everything past 0 works. Okay. So I couldn't, this program in Smartboard doesn't let me draw radicals and fractions. But this is, it should look right in your notes. So this is the square root of 2 minus 3x. Let's just write it this way. It'll look like that. so what's the problem? Well, it's an even root. And so I need to solve 2 minus 3x is greater than or equal to 0. Okay, now I want to make sure everybody hears me on this. When I ask you a question like we're about to solve here on test 1, I want to see all the work that I am showing you. I want to see an inequality, not an equation. A lot of times on test 1, students will give me an equation here. And then the inequality symbol just somehow gets tacked on at the end. Don't do that. This is answering a question here. I want you all to understand the question. What kind of numbers are greater than 0? Positive. Yeah, not all reals, but positive numbers, right? And then there's one number that's going to make this equal 0. That's what that statement says. That's why you have to show me an inequality here, because we're figuring out what makes the expression under the radical positive or 0. Okay, so how do I solve it, guys? Do what? Subtract 2. Okay, question?
So the problem will look like that, or what you wrote to the left?
This is you will have a function, and you're finding the domain of that function. This is how you find it.
Okay.
You set up an inequality. Okay?
We don't do the opposite.
I'm subtracting 2, because that's a positive 2, so I'm subtracting 2 from both sides. And with inequalities, I like the variable to be on the left, because we Americans read from left to right. We tend to read it wrong if we get our variable on the other side. So even though we got to deal with the negative, I'd rather you keep the variable on the left. Okay? All right, so it's a positive 2, you see that? And it's got something subtracted from it. That's why I'm subtracting 2, because that would be 0 minus 3x. So we just get negative 3x. And 0 minus 2 is negative 2. And then you're going to divide by negative 3 and do what? Good. Turn the sign around. If we had more time, I'd show you why you have to do that, but yes, I mean, that's the process, but I would love to show you why that's true is what I mean. Okay, so let's do a picture of this. And I do think it's with the even root problems and the rational functions, I think a lot of you would benefit by drawing a picture. Yeah?
So the negative from 2 just disappears also?
Yeah, because it was a negative divided by a negative.
Okay, yeah.
So that's positive. All right, so 2/3 is the only number that really matters here, so I'm just going to place it on the number line. So I'm just going to put it right there. This is saying x is a number less than, which direction is that from the 2/3? That's this way, right? So less than or equal to. So that means we would be using a bracket. So there's a picture of the group of numbers that are acceptable. And this is your answer in interval notation, as you say negative infinity, because there's no bound to the left, 2/3. Okay? Now, that's called interval notation. We should also mention set builder notation, because that's sometimes used, and I think you're going to encounter both in your homework. So that's interval notation, but here's set builder notation. You put a set bracket, and then you put the independent variable x for domain. If we were talking about range, we'd put y here. But since it's domain, we're putting x. And then you just put a bar there, and what's on the other side of the bar is the condition to be in this set. So this is saying the set of all real numbers x such that x is a number less than or equal to 2/3. And then you got to close your set. It's describing what those numbers are. They are numbers that are less than or equal to 2/3.
And this is the what notation again?
That's called set builder. set builder notation. This one is called interval notation. And you'll see both. But remember, if you're talking about range, they'll do the same thing sometimes with y. Okay, let's look at this next one. This is a rational function. And so the problem is the denominator, because we cannot have a zero denominator. So what you do to find domain, you're going to solve this equation, x squared minus 9 equals 0, because what you're saying with the math is what is it that makes this whole expression come out to equal 0. And some of you might factor that one, but you can use the square root method on this. If I add the 9, I get x squared equals 9. I've got a square that's isolated. And so x is either plus or minus the square root of 9, which is plus or minus 3.
Because you square rooted the x squared.
Mm-hmm. Well, it's based on square root method, which says if you can isolate a square, then you know that the thing that was being squared, which is the x, has to be the square root of the other side, or its opposite. Okay? That's why you get a plus or a minus. Okay, so let's do a picture. I'm going to plot those two numbers that are not allowed on a number line. But remember, every other value is allowed, because nothing else makes that denominator equal 0. Okay? So what I do is I put back-to-back parentheses at the values that are not allowed. This is a picture of it. But every other number is allowed. So if you'll do the picture, then look at your picture and come from the left and describe the intervals. So here's the domain in interval notation. So come from the left with me. Negative infinity until, yes, negative 3. Stop. That describes this interval. What does that mean? It means any number in that interval works. If you come in here and you plug in and you make your calculation, you're going to get a number back. Okay? What's the next interval? Yes, a lot of times people will forget this interval, so be careful about that. So negative 3 to positive 3. So all of those numbers. So does 0 work? Yes. Yes. Look, 0 over 0 squared minus 9. What's that going to give me? 0. 0 is a number. And then what's that last interval? Good. 3 to positive infinity. Okay, now set builder notation on these is a lot nicer because you get to just go the set of all x such that x cannot equal negative 3 and 3. So what that means is all numbers, just not those two. Okay, now I want you to be watching out for on these next ones. I want you to be watching out for the ones that we said are all reals. There's no problem. Is that recognizable? What type, what category that we looked at a little while ago? What is it? It's actually it's got a cube. That makes it not quadratic. So it's a cubic, but it's a yeah, it is a polynomial. Good. So remember, domains everything. Okay, what category is this one that we mentioned? Absolute value, right? Absolute value. You don't have to think too deeply. If you recognize that, you know It's everything. Okay? Why? Because you give me any number, I'm going to triple it, subtract 7. If it's negative, I make it positive. That's always going to produce something. Yes, sir.
Number 3 is all real numbers because it's a
Polynomial.
polynomial.
And see, what are you doing to the input? You're cubing it. Here you square it, multiply it by 5. Here you subtract it, and then you're adding 1. That's just always going to produce something. No problems. Okay? It always produces a real number. Okay, now I want you to think about this one carefully. It kind of looks like, oh, that's rational, so we have numbers that won't work. But talk to me about it. What's the process? That's the process, right? Set the denominator equal to 0 and solve. What do y'all think? Are there numbers that are going to make that true in the real numbers? Anything going to make that come out to 0? What are you doing to your real number? And then there's no way that's going to come out to 0. And you had these in the first homework set. You know, if you try to solve it, you get x squared equals negative 1. Remember when you put in DNE? Okay, different situation. What the DNE tells us here does not exist is that there's no problems. There are no numbers that will make this come out to 0. So what is the domain then? What works? You're not sure? Okay, go back to the beginning. Domain is always all real numbers, unless there's some that cause a problem. It's all real numbers, right? Because there are no real numbers that are going to make that denominator 0. That could be that could be a problem, right? But it's not a problem here because there are no numbers that make that denominator 0.
So that ends with the NE.
No. The answer. You got to remember what you're doing, okay? In the solving equations homework, you were solving equations. This equation has no solution in the real numbers. But we're using this to answer a different question. We're figuring out if there are any numbers that make that denominator 0. There aren't. And so all real numbers work. Let's plug in one so you guys can wrap your minds around this. Because the domain is everything. So you guys give me a value. Anything. 2. Okay, let's plug it in. What is g of 2? 1 over 2 squared plus 1. I'm just using my rule. Input is 2. I'm finding the output. 1 over 4 plus 1 is 1/5. Is that a real number? Yes. See, so your 2 produced a number. That's the point. You're coming up with all the numbers that will produce other numbers when you plug them into the rule. So if there's a denominator, the problem comes if the denominator can be 0. But what this shows is it can't be 0. Therefore, there are no problem values. Everything works. Give me another number. Square root of 2. Okay, what am I going to do? I'm going to square it. I get 2. Add 1. I get 3. Get 1/3. Everything else works. Everything works. Doesn't matter. We could go like this for the rest of our lives, right? With different numbers. Plug them in. They all produce real numbers. Okay? See, you know, I'm not sure why people get sort of stuck here, but I think it's because with algebra, a lot of times you just kind of get into the motions and you just kind of go, well, what do I do? What do I do? What do I do? You got to understand what we're asking here. We're asking what values are allowable. So you use some other algebra to answer that question. And what we just showed is everything works. There isn't any problem numbers that are going to give up a 0 denominator. Okay. Oh, go ahead.
Would we have to ask, answering the interval, how would the interval notation would be just the negative?
Oh, I didn't do that, did I? Yes, I did. Negative infinity to infinity. It's all reals. That one's all reals. So sort of start with the assumption, all reals. Unless there's something that causes a problem. So with even roots, the problem is negatives. With fractional functions, they're called rational functions, the problem is if you can have a zero in the denominator.
What would this set builder look?
Set builder we're not going to talk about with all reals. You guys don't need to know that one. Okay. Remember, the numerator can be 0. It's the denominator that cannot be 0. So, you practiced solving equations that look like that denominator. We're going to set the denominator equal to 0, and we're going to see if there are real numbers that make this statement true. Okay? So now you got to go back and remember, what do we do? Do what, guys? What's the first step in all factoring? GCF. Factor out the GCF. Okay, and you're going to set your factors equal to 0. So we do have that 0 doesn't work. And look, if I plug in 0, do you see I'm going to get 0 in the denominator? Okay, so you can't do that. You can't divide by 0. So that's not allowed. Now, this is factorable, so let's factor it. X minus 5, x minus 1. If you guys will check my middle, you'll see negative 1x, negative 5x gives me the correct middle. Set the factors equal to 0. So we get 5 and 1. And so this is really yucky with interval notation, but there are 4 intervals that we have to talk about because there's 3 numbers that don't work, because all 3 of those would give me a 0 denominator. So the picture, I'm going to do my picture a little bit different. Let's see, I would put zeros furthest left, then the 1, then the 5. Instead of doing the back-to-back parentheses, because that's kind of messy, let's just put an open circle here to indicate we're not going to include those. But we do want to include everything else. Remember, this is just a picture to help me write the intervals. So there's 1, 2, 3, 4 separate intervals that I have to include for this domain. So the domain, let's start from the left, is negative infinity to 0, 0 to 1, 1 to 5, and then 5 forever. Yep, that just throws out those 3. Okay? Now, I'm going to make you put your thinking caps on this next one. I know some people are still writing, so let me let them finish. Set builder, you would just say, yeah, you're just going to go x can't equal 0, 1, or 5. So much nicer on that one. Guys ready for a little bit of a challenge? Okay. So before we look at the next one, I just want to remind you, what's the process when you have an even root? What is it you have to do if what you're doing is finding domain? You take the whatever's under the square root and you set it greater than or equal to 0, because what does the square root of 0 give you? 0. 0 is a number. It is a real number. So the number that produces 0 here works. It gives me back a real number. And we've talked about the problem with fractions, so I'm going to throw you a curveball here. I'm doing both. That one's a fraction, and it's an even root. So talk to me about it. What do you think doesn't work? Can anybody see a number immediately that doesn't work? 5 doesn't work. Good. Look, f of 5, what does that do? That gives me square root of 0. Square root of 0 is 0. This is undefined. That is not a number. So what you just told me, what you were showing me with that, is 5's not in the domain for sure. Okay? I'm going to throw in another number that's not in the domain, just so maybe that'll help people understand why we're doing what we're doing. Okay, positive 1 seems like a reasonable number to plug in. Let's plug it in and see what happens. We get the square root of negative 4. What's the square root of negative 4 in the reals? It's not defined. You see that? So 1's not in the domain either. So 5's not in the domain, 1's not in the domain.
It's 2.
Is it? 2 minus 5. What's the important value here? Where do things change? Where we start getting numbers that work?
After 5.
Yes, after 5, because then this is going to be positive, right? Okay, good. You guys are getting it. Yes.
Technically speaking, the 1 over square root of negative 4 would be 1 over square root over I square root 2.
Yes, it is what's called a complex number.
Yeah, but we're not there.
But we're not doing that. Yeah. And we don't talk, that would be complex functions, which is way beyond 1105. We don't even do that.
Oh, we don't do anything.
No. We will solve equations that have to do with complex numbers, but we're not going to have anything to do with functions in complex numbers. We're always talking about real valued functions. Okay, so here is the thing. Instead of saying I need x minus 5 to be greater than or equal to 0, I would say what? I need it to be greater. Yeah, it is greater than 5 because the expression needs to be strictly positive, right? It can't come out to 0. So I'm not putting the equals bar. Go ahead.
You just put greater than 5 because it needs to be greater
Right.
than 5 to.
Right, but what I'm trying to get you to understand is you're using algebra to get the answer. I know you can see it now. You can see that anything to the right of 5 works. But the process is important because some of you are going into some harder stuff. And you got to understand what you're doing and how you get there because you can't always just look at it and tell. Sometimes it's a fraction, right? And sometimes it'll be to the left of the number. We saw one of those instead of to the right of it. So that's why it's important to solve the inequality. Okay, but I did not include the equals bar because it was in a denominator. So not only did it have to be positive, it could not equal 0. And so our final answer then is that the domain in interval notation is 5 to infinity. Because it would, remember, we saw 5 doesn't work, right? And that's because it's in a denominator. So denominators can't be 0. And this is called a radicand. Okay, the radicand of even roots can't be negative, or, but they can be 0, but not if they're in a denominator like this one. Yeah.
Wouldn't it be a bracket 5 infinity and then parentheses?
No, because 5 is not included. Remember? 5 doesn't work. We showed it.
But doesn't a parentheses mean you do include it?
No, parentheses means you don't include it. That's where it ends. Okay? Bracket means you do include it. All right. So we can take a little deep breath because now we're going to do zeros of functions, which is a little bit easier. I'm going to